So before we get started, just so I can gauge, who all is in this audience, can you raise your hand if you're a front-end developer? And if you're primarily focused on the back end, hands up. And raise your hand if you know what cross-site scripting is. Okay, fantastic. So we can touch on that, but focus on other areas. So I'm not going to be tying this to any particular framework, but the purpose of this talk, and I do a lot of speaking at conferences, and I've been submitting this talk for 2 years, trying to get, conferences to take it in. I'm so glad that they accepted this one, simply because A, this is a really interesting topic, and B, as we see with the recent Equifax breach, it's becoming a more and more serious issue. Did you have a question? It's hard to hear me. Let's try moving this up. Is this any better? Or when we get a sound person, they can turn it up as well. I'm also going to be kind of demonstrating some hacking techniques. So if you have, I'm not going to do, I promise you'll see everything I'm doing on the screen. But if you don't want to potentially be releasing some basic information like the Wi-Fi networks you've joined recently, now is the time for it. Don't everyone go on airplane mode, because then it's not going to be any fun. Nope. Well, we'll see. You leave your phone on. We'll see. We'll see how that works. All right, so it is 11:15 by that clock at least, and I've got a lot to go through, so I'm going to get started. First off, my name is Mike, and what I do in the area is I work with teams across a variety of different companies to train their developers, primarily web developers. As you can see in this conference, we've got something like 6 parallel tracks. There is so much to keep track of, so much that you need to stay up to date with. And so the purpose I serve is I'll come in and I'll work with the team to do a 3-4 day workshop, completely bring them up to speed with the latest advances in topics they care about, rather than them having to watch all the GitHub issues and stay on all the mailing lists. And it's sort of a condensed upgrade. Basically, I'm like the upgrade patch for developer teams. So if you know people that work at these companies and several others, you probably know people that I have worked with within the past couple years that I've been doing this. And today specifically, I'm going to be talking about one of the big problems we have in the web development world. First off, security is kind of like insurance, or like product teams look at it like insurance. They start to care about how good their security situation is when something goes wrong, right? So you really take the closest look at your homeowners or your auto insurance policy when someone hits your car or when a tree falls, on your garage. And it's sort of an afterthought in that respect. And it competes for attention against features and bug fixes and all of the things that, are on your quarterly goals, right? Security is often not on quarterly goals unless you have a team dedicated to that. Web developers in particular, when compared to folks that work on algorithms at your various companies and the people who manage your deployments, like your ops or your SRE team, web developers have fallen seriously behind in terms of keeping up to date with the sophisticated, ever-advancing different types of attacks, right? So cross-site scripting has been around for 20 years. We need to worry about more things these days, or more sophisticated attacks. And the attacks are getting worse, right? So early September, 147 million people's, let's just call it like everyone who's borrowed money in America, all of their personal data was released through a breach at Equifax, through an Apache Struts vulnerability. Yes?
That happened, someone was holding, that's when it was revealed to people.
That's when it was revealed, but this was, so some details about that. It was an error, not only an Apache Struts vulnerability, which was known and which they'd failed to upgrade and to mitigate that problem, but they had a plague of other problems where a web application had direct access to the database holding that data. And then has anyone here tried to do a database backup before? So when I try to create a clone of a database that has a few thousand records, that takes a while, right? You see your CPU is at 100% on that machine as it starts to build that database backup. 147 million records that should have sent off a signal, what is this machine doing? So it was a failure on many parts. However, all of those failures were sort of in the web app development side of things. This was a design flaw and a patching problem where they weren't up to date in their dependencies. But things are getting worse and worse and worse because all of our information is in the cloud, and developers are not up to date as to what are the best practices and how do you set things up so this can't happen. And finally, I will definitely convince you, I'm going to take questions at the end just so we keep going here. The barriers to staging an attack are much lower than you think. So the public perception is you need to know Python and you need to know about specific vulnerabilities in an app in order to attack it. It's more like you need to install something that has an app store, and then you download some apps that will automatically launch attacks across a whole range of IP addresses. So you don't really need to know much. You just need to be motivated enough to watch a 30-minute YouTube video, and then you're good to go. So just because it's nice to have a story to go along kind of a talk like this that touches on many issues, here's our example app. It is an online bank that you have a bunch of accounts. Is it too soon? So you have a bunch of accounts, and you have the ability to transfer money between accounts. This is going to use cookie-based authentication, so there's some sort of session ID, and the server looks to the cookie to see, is this an authenticated user? Which accounts are they authorized to access? And we need to support IE9 and newer browsers. Now, in terms of the different things we're going to look at, 3 network attacks and 3 client-side attacks. Client-side attacks simply mean that we're using the client-side app in some way to try to gain information or be destructive in some manner. So first, let's talk about a man-in-the-middle attack. And the scenario we're looking at here is one of your users is accessing your application, and they're on a public Wi-Fi network like Starbucks. So I'm going to take advantage of a few things. The first is that when you join a public Wi-Fi network, your device is going to remember basically forever until you clear it, the list of networks that you have joined. And does anyone here use iCloud or Google sign-on to sync data across your devices? So that list of networks is also synced across your different devices. The second thing I'm going to take advantage of, and I'm going to start it up right now, just as a little demo here. So I've got one of these little attacking devices here. I'll tell you more about this in a moment, but it's this thing here. It's a little Linux box that runs off a cell phone charger with 2 Wi-Fi antennas. So your devices are constantly broadcasting where you've been, right? So I'm not getting any of your private information. I'm just simply listening to all of the chatter that's coming out of your phones and your tablets and your laptops. So what this is letting me do here is every 15 seconds, it's going to go and basically sweep the room or anyone within range and let me know, all of the different networks your devices are asking to join. So we've got a lot of these PayPal guest and conference and things like that. Usually we'd get a couple more here, and if I scan for longer, I'd get quite a few more. So this is someone's home network. What we can do is grab this conference network, and we'll say we want to add this SSID to another next step. It's just accumulating a list here. You see we've got a bunch of MAC addresses of things that are not on a Wi-Fi network right now, but they're willing to join if the right network presents itself. So once we've got that, we can, I'm going to just have to add it here. What's the Wi-Fi network here? Is it conference? So I'll add that, and I'm going to start basically getting information that relates to that particular network, right? Who has joined this thing? I'm going to let this run for a little bit, and we'll take a look at it in a few minutes. But what I did show you was that your devices are announcing networks they wish to join. So that's number 2 thing I'm going to take advantage of. Number 3 is when you join a network, typically you trust that router as your DNS server. This is the very important first step of establishing a network connection of any kind, where you translate a host name into an IP address. Seems like a pretty important thing to trust to a strange router. So some people like to point to Google's DNS servers, 8844 is the other one. But the problem is you're going to run into trouble on public Wi-Fi networks, because to get screens like this, where they ask you to agree to their terms and conditions, they actually, technically it's an attack, right? They launch an attack on anyone who's joined that network, and it is called DNS poisoning, where you're not getting legitimate DNS results. Every host name will route you to this particular page here, so that it's sort of standing in the way. So we've all been here, and you try a couple HTTPS URLs, it doesn't work. You find that one plain HTTP URL in your bookmarks, and you'll finally hit this page here if it doesn't pop up automatically. Okay, so taking advantage of those things, what will happen is I will take the role of the attacker here. So I will come into the Starbucks, I'll sit down. If you see me come into the Starbucks with something that looks like this little black thing, airplane mode. So what's going to happen is I'll join the network because I want an internet connection. Wi-Fi Pineapple. So, and then I will do the same thing I just did, which was like scan the area to see, like I just found that some good networks to imitate here would be Conference, PayPal Guest, right? A lot of people around here want to join PayPal Guest. So, but let's say I'll create a different one, Airport Free Wi-Fi. Probably some of you have joined Airport Free Wi-Fi at some time. Then I'm going to send a bunch of garbage packets to this client that seem like they're coming from the server. They really haven't. They're coming from me. And that'll cause that connection between this target that we're after and the router to drop. And at that point, their phone's going to start scanning to try to find something. Odds are, if this attacker knows what they're doing, they have a really powerful antenna, and so it's a nice full signal network. That's the one that device is going to join. They hop on, and now this person has positioned themselves in the middle. Now this can all be automated. I just showed you this little device that was able to start this process pretty easily. And at this point, all plain HTTP traffic can be eavesdropped on or tampered with. So this is the kind of setup that you need for it to stage this kind of attack or to do So this is the kind of setup that you need for it to stage this kind of attack or to do penetration testing. You should know it is illegal to like man in the middle someone who doesn't have your permission. It is interesting to play with these things and to learn about it and to do it to yourself. So I'm not telling you to go and do this at a Starbucks. What we have on the left is a powerful Wi-Fi adapter. So typically the ones that are in your laptops are 120 or 200 milliwatts, and that is the radio strength. This is because this monster here, that's 2 watts. That is any larger than that, and you'd have to get a license from the FCC to have that working. And it drains battery like you wouldn't believe. Like you can watch it go down. But it is really powerful. So if I had that here, I would get all of this PayPal town hall and probably across the street, as that is me casting my net to try to get people to connect to me. On the right side, we've got this Wi-Fi Pineapple. It's a Linux box that has 2 Wi-Fi adapters built into it and 2 antennas. And it is built for this kind of attack where one antenna gets on the internet and the other creates the network. And so it's meant to get people to start routing through it. There are like wired network variants of this. It actually comes with the handwritten do not remove tape on it. So this is my favorite. It's an accessory for this device here, where you would just get a phone charger of some sort and stick the Pineapple to the wall, cover it with this thing, because it's got power. The lights will light up, and if you push the button, it'll actually beep like a carbon monoxide alarm. So short of knocking all of the plastic stuff off of the walls with a broomstick, you're not going to find this thing. And even if we go so far as to say we're always like, I've got a corporate network, I'm always using a certificate to join this network, and there's no way you're going to be able to imitate this, I could use what's called a femtocell. So this is something that your cell service provider is eager to subsidize for you, to rent to you. It is designed for situations where maybe in a parking garage or in your basement, you have a weak signal. This sets up like a mini cell tower within your home. So you'd plug it into your internet and it creates, think of it like a Wi-Fi router, but instead of Wi-Fi, it's LTE or it's 3G connection. The difference is you don't have a choice as to whether you join this, right? There's no name to this network. You don't click to say, I'd like to join airport free Wi-Fi. If your phone is on and you're near this thing, you will join it. Even if it's not your house and you're just walking by the house, you'll hop on this. The reason is these are really cheap relative to those cell towers and they're less in demand, right? There are fewer people competing to join these things. So in order to kind of balance their load across their network, their cell network, they would love for everyone to hop on these whenever possible and to like alleviate the pressure on the public antennas that have to go over an entire neighborhood. I mean, it depends what's in the area. So typically it's going to be in a basement, right, or something like that. So it'll contain this thing, but it'll go way out beyond your house. You didn't ask, but I'm going to give you some more information. About $250 on eBay, and yes, you can write over the software quite easily and turn it into an attack platform. You could put it in a car and just drive on the highway, and people's phones will just pop right on this thing. So the way to not join this is airplane mode, all the time.
So if you put it like in your car, there must be like some prison term associated with it, right? This is highly illegal, right?
Yeah, but I mean, have you ever tried to report a crime like this to the police? They don't even know how to categorize it. Yeah, so yes.
I come from the hamburger world, so I know a few things about how to catch these guys. But okay, but later.
You may know how to catch these, but let me say that this kind of thing happens all the time, and the authorities do not typically have the focus on this type of crime that would be required to get you. So the solution to this is to encrypt all of your data while it's in flight. And the concept here is instead of just sending messages out in the open that anyone can read, we use a secret to make it so that, yes, you may read that message, but it's going to be gibberish unless you know the secret way to decode it. Part of this mechanism involves certificates which verify that we're talking to the domain we mean to talk to. And you can get Sorry, I'm going to just take questions at the end because I don't want to fall behind here on my time. We're going to, so you can have domain validation certificates and then enhanced validation, which are the green bar certificates. You should know that there's nothing technically that makes these any more secure in terms of algorithms and things like that. It's just a more involved process that's required in order to obtain one. For example, if you want to represent yourself as a company, you have to submit your articles of incorporation or another similar document, and that's the only way you can obtain one of these in theory. In theory. We're doing pretty well at encrypting the whole web. A big part of the drive forward has been an organization called Let's Encrypt, which gives people certificates for free and tries to make it easier to get these things. Hopefully, in the next 5 years or so, it will be something that comes with every web hosting service that you buy, and that it won't be like getting a certificate for your domain will be as easy as possible, and it will be almost automatic. So I'm going to take a moment just to talk about how this works, because if you know how it works, then you know what are the secret things that you need to protect, and you'll also understand, what is keeping you safe here and how it's keeping you safe. So for HTTPS, there are two types of encryption we have to think about here, something called symmetric encryption and then something called public key encryption. Symmetric encryption is really fast. So I want you to imagine this, like one type of symmetric encryption is called a Caesar cipher, where we just take every letter, imagine they're on a wheel, and we rotate the wheel 13 characters. So you might know 13 is my encryption key there. If I know the number 13, I can create a message by changing A for whatever's 13 letters after A. And if you know 13 is the key, you can rotate that back and get back to the original message. But that number 13 is the information you need both to make a message and to read a message. It's really fast relative to public key encryption, and there's no limit, practically, for how big a piece of data we can encrypt. The problem is, if I'm going to send you a secret message, I first have to come to an agreement with you that we're going to use the number 13. And if there's a man in the middle, they're going to be able to see that number 13, and like we have defeated the purpose of doing this in the first place. So safely sharing the key is the big missing piece of this puzzle, and that is where public key encryption comes in. So the math behind this is much more complicated, and it is much slower, but the key benefit this brings us is it separates the permissions, it separates capabilities, meaning you can have a key called the public key that can only be used to write messages. It's pretty much useless in terms of being able to read messages. The private key is what you need to read messages or to generate that public key. So think of it like the private key has all of the ingredients. The public key has only those ingredients that one needs in order to read and is missing a few key things. Only the ingredients necessary to write a message, and it's missing a few key things that are needed to read. RSA is the most popular public key algorithm by a fairly huge margin. And exponential math is involved, and because typically we're working with floating point numbers or double precision numbers of a certain precision, you get to a point, like you can only encrypt so much data before you start losing things due to rounding errors. So in order to convince you that, to help you understand how this works, first I need you to understand that although some math is the same level of difficulty in either direction, like 6 times 5 is 30, or 30 divided by 6 is 5, right? Those are both fairly like the same level of difficulty. If we thought about squares and square roots, where squares are making encrypted messages, square roots are decrypting those messages to get back to the original. Everyone in the room, if I gave you a simple calculator with only plus minus divide and multiply, yeah, then everyone could do 17.47 squared, or you could do 17.47 times 17.47. Pretty easy. Getting the square root of this number is a little bit more difficult. So we see there, okay, we've got, it's harder to decode than to encode. Now, RSA takes that to the extreme. The public key is something based around the product of two huge prime numbers, and the private key is those individual prime factors. You need the individual prime factors in order to read messages, but you only need the product of them to write messages. So brute forcing, like attempting to guess this private key, involves trying to guess two gigantic prime numbers, and they occur at random intervals. No matter how big numbers get, prime numbers occur with reasonable frequency in an unpredictable way all the way up through all of the numbers. So it's really, really hard to guess these, and it would take thousands and thousands of years with tremendous computing power to crack one of these things. So that is the basis for this, right? You can also use a private key to sign a message, and just think of that. So I'm talking about math in a forwards and backwards direction, in that the encryption and decryption functions are inverses of each other, right? So like encrypting something and then decrypting it gets back to the original value. It has to work that way. That's the whole point. If we take a plain value and run our decryption algorithm on it, so let's say our value is 64, and we know square roots are really hard. We're going to pretend we can't do 64 in our head. So to sign this value, to demonstrate that we, the holder of this magic square root decryption algorithm, we have been here and we certify this thing and we've processed this file, and it had to have been us. We would take something that's already plain text and we would decrypt it. It's not necessary to decrypt it to read it, but we're going to do it anyway. Everyone in the room has this public key that they typically use to write messages. But remember, because these are inverses, we can take this signed value, which would be 8, and we'll square it, because that's our encryption algorithm, and we get back to this original. So that's something that only someone with this private key can do. Just think of it as decrypting one step too far and then encrypting it again will get us back to the original, and we can verify that someone has signed this thing, right? And only they could have done it because the private key is required in order to perform that operation. Okay, this is the maximum density of this talk, so everyone can take a breath here. We're going to put these into practice, and we're going to talk about what's called the TLS handshake. And when you establish an HTTPS connection, this is what you're doing. So we start with public key encryption just to exchange keys. This is slow because, again, the math is really complicated, but it's what lets me package something up so that I can generate a random password, encrypt it, and then send it to somebody safely, and parties along the wire cannot read it. So this process begins with a server sending a client, like a browser, a public key, which it is eager to distribute, that's fine, and its certificate. Client and server then compare what is called cipher suites. So in the case of like this rotating Caesar cipher I just described to you, that would be a cipher suite. Like I can do Caesar-style decryption, encryption and decryption. The most common one here is called AES encryption. If you've seen that before, that is what most HTTPS connections use these days. So the browser generates that. It's called a session key. And then it encrypts it with the server's public key that can only be used to write messages. Only the server can read something when I encrypt it with that server's public key. And then I can send that key over to you, and it'll, like, a man in the middle can read this, but it's gibberish. Without the private key, they can't make any sense of it. So once that's established, then we can use this cheaper, more efficient symmetric encryption to start communicating without anybody listening. So just to explain it one more way, here's how this works. The client tells the server it would like to communicate securely, and it lists the ingredients for a Manhattan as the different ciphers that it uses. The server is going to say it's going to pick one, and they can have a bias for more secure or more memory efficient or whatever it is, but they come to an agreement as to which cipher they're going to use. The server is going to provide its certificate to the client, and certificates are signed by people we trust, right? These are certificate authorities. If you've heard of companies like Komodo or VeriSign, these are people that hold their private keys very closely, and your operating system in your browser comes installed with their public keys, and those are what we would call like trust roots. So if we see a certificate signed by one of these people, we know that is worth trusting. It's also going to send its public key to the client so that the client can then send messages that are readable only by the server. So the client's going to look at its trusted roots, look at one of these private keys for like VeriSign would have been used to sign the certificate, right? Basically, remember that's decrypting one step too far, and they can take this public key and they can say, yes, this is a Komodo certificate, it is valid. It's going to generate the password. This is that symmetric encryption key, right? And it'll encrypt it so only the server can read it, and then it'll announce that from this point on, everything that it says is going to be secret. And the server's going to agree and say everything that it's going to say from this point on is secret, and then we have established this TLS handshake. So this screen here, this actually represents every part of the TLS handshake official requirements is represented here in some way. That is all there is to it. So this is what happens. And by the way, this session lasts longer than one request, right? It can last a couple hours, but you only need to perform this handshake every so often, and then a new session key will be generated, and those are sort of like disposable passwords. So let's say we put that in place, and now the man in the middle can't read anything, right? They can see these packets going by, but they can't make any sense of them. So what's going to happen then is we'll use an HTTPS downgrade attack. And essentially what happens here is we take advantage of the fact that plain HTTP links, nowadays, if you have a secure site, they're going to redirect to the HTTPS equivalent. So what we'll do is we'll get in the middle and we'll say, here comes an HTTP request. We'll establish a secure session and do that TLS handshake as the attacker to the server, and we'll maintain a secure session there, but we'll like take away that redirect. We'll make it so that the user is still in a plain HTTP connection situation there. And at this point, you have to notice that the padlock's missing from your URL, and 100% certain nobody in this room is that vigilant. Like, you could be hit with this. Yes? Yes, HTTPS everywhere is a browser add-on you can install. So this will have a bias for establishing an HTTPS connection over plain HTTP, and you'll actually have to disable this in the event that someone would try to stage this kind of thing. There are other precautions you can take as a developer in terms of upgrading your site. One is look at upgrade and secure requests on your own time for content security policy. This helps you kind of make it so that your users are spreading around secure URLs instead of insecure ones. However, we can still take this a step further. Let's say you have that add-on installed, and what we can do is take advantage of an extension to TLS called server name indication. So typically with TLS, you do that DNS resolution, right? You say, Silicon Valley Code Camp. I have a host name, give me the IP. And then you're going to try to handshake with that IP address. And it has to tell you, here's the certificate for me, and I am Silicon Valley Code Camp, right? You don't indicate that you're trying to connect to that particular domain. It has to come back to you and say, and affirm that, yes, that's the right host name. So companies that, this is something that's very important, server name indication. It's important for companies that have multi-tenancy for hosting, where you have one IP that's responsible for a variety of different domains. So if you use Cloudflare, for example, they depend on this like crazy. So one IP with multiple host names on it, you kind of have to announce that you're trying to connect to Silicon Valley Code Camp when you initiate that connection. And as an attacker, that's all I need, right? I can generate a certificate on the fly and try to establish a secure session with you. I'll do the same thing with the server that I was doing before, right? Do my handshake and so on. But what I'll send back is a forged certificate that's not signed by one of these trusted roots. And you'll get a warning like this, right? Saying something wrong with this certificate. So show of hands, what percent of people do you think click through this? More than 5%, hands up. More than 10? 15? 25? Interesting. Okay, so we've been training users to ignore this. 44% of 400,000 or so top websites, this was from a Carnegie Mellon and Google study, had a lot of websites had certificate errors. Either they were expired or the domain wasn't set up correctly, where the certificate was for one domain, a legitimate certificate, but the host name was wrong, right? Maybe you hit a github.io URL, but you're supposed to be using this custom domain name. It's the wrong certificate in place. So users see these warnings habitually, and as developers, we see these warnings even more. Every big tech company has internal certificate warnings all over the place. So before Chrome started to make massive improvements, 70% of people were clicking through these warnings and saying proceed anyway. After the improvements, it's still 44%. So let's call that half. Half of people regularly click through these things. And by and large, they don't really understand what that means. When they say proceed anyway, they don't really understand what risk they're taking on. So I propose to you that for us as application developers, it's in our interest to remove this responsibility from users. Through faults of our own, they are not well equipped to make these decisions anymore as to whether they should accept a flawed certificate or a plain HTTP connection. So what we can do in order to reclaim that ability to make that decision is to add a new header to our HTTP responses, and that is called Strict Transport Security, so HSTS. And on the second line here, there's an example of this header. What we're instructing browsers to do is to remember for a certain amount of time that you are forbidden to make plain HTTP connections to a certain domain. And if there's a certificate error, stop users cold and don't give them a chance to proceed anyway. Make sure when you apply this to use include subdomains, because if you don't, I could just man in the middle a subdomain and still, there are a variety of cookie-based attacks that I can use on an insecure subdomain, even if you've locked your main domain down, your top-level domain. So this is great, but it's an HTTP response. So a user has to hear from our server before it'll follow these instructions. And a man in the middle could just get there first, right? If your initial connection to a server happens when there's a man in the middle, all of the automated attack scripts will strip this header off, right, and make it so the browser never receives these instructions. So we have an incredibly elegant solution to this. You go to hstspreload.org and you add your domain to this. There are about 80,000 of them at this point. And every browser, every evergreen browser, bakes this as a mega huge array into their source code. So the next version of Chrome or the next version of Edge or Firefox or Safari, they will ship with an array of domains that browser comes installed knowing to never trust an unsafe connection. Obviously, this is not sustainable, but it's the solution we have now. So the warning that users get, you'll note that, so in this case, PayPal was a really early adopter of this. I think they're number 11 out of those 80,000. The user has no option to click through and say proceed anyway. The error they get is stopping them, and they're just asked to try again later. So the man in the middle would maybe succeed in annoying this user, but the user is never put in a position where they think that they're operating with the genuine site. So with that, I'm going to proceed on to trust compromise. We'll go back to the pineapple in a second. But what I'm talking about here is what happens when a certificate authority is somehow compromised. Their private key is leaked. So the most recent major event that happened here, or the most recent public one, I'm sure it's happened since, was in 2015 where the Chinese government got a hold of an intermediate certificate authority's private key. And they were able to, so this is a private key where any certificate this thing signs, your devices, your browsers, they're all eager to trust. So there were wildcard Google certificates and tons of other certificates floating around on the dark web signed by this thing. And the typical way you combat this is everyone tries to release a new version of the browser or a new version of the OS that revokes trust for this certificate authority. However, this has happened and it will continue to happen. So we need to build into our apps some defense for this. Another typical thing that happens here is us as developers, have you ever trusted a self-signed certificate? Raise your hand. Okay, odds are that was a root certificate. The simplest way to generate a self-signed certificate gives you something that can also sign other certificates. If someone gets a hold of the private key for that trusted root, they can create new certificates for your bank, for Google, any of these federated login sites. So that is another common way of doing this, right? So if everyone in a given company has signed a root, if you work for a big tech company, they've probably had you trust something so they can make their own certificates internally. They can eavesdrop on or tamper with HTTPS traffic between you and anyone because they can use that root to create certificates on the fly for any domain. There is a defense for this, but not if you've explicitly trusted a certificate. So we're just going to talk about the certificate authority compromise. But I say this, you should clean your certificates out. Every time you trust something, that is a big deal. That is total HTTPS means nothing across all domains. So heads up. The way you would deal with it if it's something you didn't explicitly trust, right? These are true certificate authorities, is you can add a new HTTP response header. Similar to HSTS, it gives browsers instructions as to what they're allowed to do, what they're allowed to trust, right? So in this case, you would add a fingerprint of your public key to this header, and then browsers will validate that the certificate they get as part of that TLS handshake is not just a certificate signed by someone they trust with the right name, but it is the one. It is the one. You fingerprinted it, and it's not simply an approved one. It is the right one, right? Because I can go and I can get Komodo to give me a certificate for my domain, and I can go to VeriSign, and I can go to GoDaddy, and they're probably reselling someone else's certificate. I can get as many as I want. I just simply have to prove I own this domain, and everyone's eager to sell me one of these things. But here you could say, this is the true one, browser. You're only allowed to trust this specific one here. Don't trust any that are generated by other people. So this would save you in that certificate authority compromise. Unfortunately, almost nobody uses this. So less than 400 of the top million Alexa sites use this. Google does, and this is why when cert authorities are compromised, they are sort of insulated from that. if you're using a browser that observes this header and understands it and follows those directions. Keep in mind if you enable this, and this is probably one of the reasons that so few people have adopted it, if someone gets a hold of your private key and you've told browsers that only this certificate is the one to trust, you're in a tough spot, right? Because you really want to get a new certificate at that point. However, the browsers are going to follow your previous orders, and like you can either use the flawed one that's been leaked out somehow, and that'll work to send HTTP responses, or you can use a new one and people are going to see errors that will, again, stop them from entering the site. So those are a couple network attacks. We're going to go really quickly through client-side attacks, and people indicated they've seen cross-site scripting before, so we're going to just skip that for time. Cross-site request forgery. Hands up if you feel like you've mastered cross-site request forgery. Sweet. Almost nobody. Okay. So this is a client-side request where we take advantage of the fact that basic authentication credentials and cookies are sent along every time a user makes a request. So if you log into equihacks.com and you've done your online banking, you have a cookie there, and that might be good for 2 weeks, right? You stay logged in for 2 weeks. If you request images off that same domain, those cookies are sent along for the ride. Those basic authentication credentials are sent along for the ride. And the server is looking to those cookies in order to ascertain as to whether you're a legitimate user and whether you have a right to access that resource. So what we could do, let's say we're in a terrible situation here. Let's pretend that Equihacks is a business that doesn't take responsibility for keeping users secure. Just go out on a limb there. And let's say they also don't obey RESTful API conventions. So they have a GET request that mutates data. So what I could do is send users an HTML email with an image tag that looks like this. That's going to make requests. In this case, it'll transfer funds from one account to another. By the time your browser attempts to load that image, and of course it's not going to come back as an image, but that doesn't matter because you're tricking users into making a request that's a legitimate user that's legitimately able to perform some operation. I can't see it from within this HTML email, right? I, the attacker, don't actually see the response, but I can initiate the process of making the request. So this is why CSRF attacks always are targeted towards attempting to mutate data, because you have no visibility into the response, but you can at least cause users to attempt to make a change, which you would then use to escalate to another attack. Even if you do use RESTful conventions, I can create a hidden form with some JavaScript that will attempt to submit this form, so you're not safe even if you use RESTful APIs. The defense for this is to add what's called the CSRF token, and this is a disposable token that is used to make one request, and then it increments in an unpredictable way. So it'll just look like gibberish. And your server will have some salt, a cryptographic salt, which is it is a secure value that is used in order to determine how this token changes with each request. So you can think of this kind of like two-factor, well, there are two factors here. One is something proving that your user is authenticated. That's the cookie. That's been there this whole time. We were abusing it, right? And we're stopped now because number two is in place. And that proves that we have the ability to run scripts on that domain. So CSRF token is typically coming to the page in a meta tag, or you keep it in local storage or session storage, something where the browser is going to require a script running on the right domain in order to access that and to put it into the request somehow. It doesn't just go along for the ride automatically on some arbitrary site. What we can do initially is try to filter for the correct request origin. Combination of origin and refer headers are used here depending on which browsers you're targeting. If you're behind a proxy, X-forwarded host is usually where the original header ends up being placed. So origin would be like your Squid or your your edge server, right? X-forwarded host is where the things truly originated from. So last attack we're going to look at is called clickjacking. And what we would do here, so say we've been completely thwarted in terms of our previous attacks. We know we have to send things through the legitimate web client, only for logged in users. We can't man in the middle anymore. What we can do is something called clickjacking. So what that's going to do is we'll set up a page on a lookalike domain here. So if you look at the URL on the right, at first glance, it's equihacks.com. When you look closer, it's not really that domain, right? So you'd buy something and set it up like this. We would take the legitimate web client, we would iframe it, and position it so that the button the user thinks they're clicking on is really this transfer funds button. So we're going to have like basically a transparent iframe. So the user thinks they're clicking on proceed, they're really clicking on transfer funds, fade that all the way out. And when the user clicks, they're actually interacting with this transparent page. And so you can trick them into, performing actions with some application other than the one they're seeing right in front of their eyes. The most severe clickjacking attack in history was on Adobe's Flash settings page. There's one URL you can go to where you can manage global Flash settings. And through an elaborate series of CSS repositioning and things, there was an attack that involved basically tricking users into setting up really low security, very permissive settings for particular domains. And then through social engineering, you could get users to click on links for those domains and turn on their webcam and basically do anything else that Flash is capable of doing. The way to combat this, there is an X-frame options header you can use. So deny forbids a frame from being embedded in another one. Same origin only allows it if the top frame is has the same origin as the frame being embedded. X-frame options, that provides an allow from whitelist. However, there is some movement towards a content security policy-based approach here, where you can say, here are the allowed frame ancestors for this thing being served up. Keep in mind, because we really care about the URLs users click on, when you're thinking about a situation with nested iframes, the one that is checked against this header is the topmost frame, right? So if you've got, for example, a LinkedIn page that's embedded inside of a PayPal page that's embedded inside of some hacker's page, the LinkedIn page will look directly at the hacker's page and use that origin as the basis for whether it should work. So this allows us to safely embed iframes in our own apps and not worry about the nested effects of everything. For legacy browsers that don't listen to this, there's a clever hack you can apply where you add a style tag to your page that hides the entire body, which when you use display none, you cannot interact with anything on that page. And only in the event that you can identify that you are the topmost frame on a page, right? That's what the self equals top thing is. Only then will you remove this style, making your page visible. So this would be your solution for IE9 and IE10, which don't support as wide a range of X-frame options settings. So you can see here, in the event that we determine we're not nested in something, we'll remove this style block, right? And our page is visible and the user can interact with it. In the event that something looks strange and we are embedded in something, we attempt to reach to that top level frame and to set its location equal to our location, effectively popping out of the frame and taking over the page. Now, any reasonable clickjacking attack is going to apply some sandboxing options to the iframe that'll prohibit the ability for the framed content to trigger navigation events through this mutating this top value. At least we're attempting to do it here, right? Even if we're stopped short, at least we're rendering nothing. So in summary, we've gone through a bunch of these attacks. I know we skipped cross-site scripting, but y'all know that. There are a lot more attacks that happen with great frequency. Even if we were just to look at the subset of things that apply to web clients, this kind of stuff is happening all the time. If you doubt this is happening, by the way, try spinning up, get a free database or something, expose a MongoDB or a MySQLDB database to the public world without a password on it, come back to it in 24 hours, it'll be full of crap. It'll be full of cross-site scripting attempts, and so there are constantly attacks going on. You don't see most of them. Some of them are probably succeeding on your app today. So it is time for us as web developers to upgrade our knowledge and to take responsibility as we write our code, making sure it's secure. So if you want to upgrade your team, I teach a bunch of different courses. Come talk to me. Come in and do a workshop. tune you all up. And in particular, this web security workshop that I teach, it's 2 days of alternating attacks and defenses where you play the role of the hacker, you crack into the system, and then the next exercise, you make it so that what you just did is impossible, right? You shore it up. And we do about 8 rounds of that until things are less ridiculous, surpassing even Equifax's level of security. What's that? I do have the pineapple running, so I'll take questions in a moment, but I'm going to check out what this pineapple's been doing. So let's see. Oh, it might be stuck. Let's see what's going on. Somebody hacked me. God damn it. All right, let's see. There we go. So I can find these are the MAC addresses of all of the different hotspots that are throwing out this conference Wi-Fi. I could then use this to move on to finding everyone that's joined onto these clients, and you get the names of people's phones. So if anyone have like Mike's iPhone or something like that, so there I could pluck you out, and then I could target you and find which network addresses are you looking for. So this is all information that you're constantly broadcasting to the world. Here's the App Store for this. You can just install a bunch of modules, and my point in showing you this is you have to have about 20, 30 minutes of motivation. I think I've lost a network connection here. That's why it's not working. But you just have to have a little motivation in order to do this. The technical skill required to launch one of these attacks is almost zero. It's like if you can manage a WordPress instance, not that requires almost zero, but if you can manage a WordPress instance, you're way beyond what's needed in order to do one of these things. So assume you're always being attacked and protect your users. Questions? Thank you.